Hello everyone, in this video I am going to discuss about AVL tree. AVL tree is a self-balancing binary search tree where the difference between heights of left subtree and right subtree cannot be more than 1 for all the nodes. The difference in the sense the balancing factor. So the balancing factor for each node should be either -1 or 0 or 1. To calculate the balancing factor, the formula is height of left subtree minus height of right subtree. So this is the formula for computing the balancing factor for each and every node. And one more thing, after every insertion, we should find the balancing factor for each node. Before all this, the main thing is it should be binary search tree. The main advantage of AVL tree is it is highly efficient when there is a high number of input data which involves a lot of insertions. So when it comes to the binary search tree, it is going to take big O of n. When it comes to binary search tree, it is going to take n complexity, big O of n time complexity. But in AVL tree, since it is going to be the self-balancing binary search tree, the AVL tree is going to take only big O of log n complexity. Why? Because every time we are just going to make it balance. After inserting each and every node in the AVL tree, we are just going to check whether all the nodes are balanced or not, like whether the balancing factor falls under -1 or 0 or 1. So when it is not balanced, we are just going to make it balanced using some rotations. Rotations will be discussed further. So since we are just going to maintain the balanced binary search tree all the time, the complexity which it is going to take for AVL tree is big O of log n complexity alone. So the searching operation also can be done in AVL tree with the same complexity, which is big O of log n. Right? So as I told you before, every time the tree should be balanced. When it is not balanced, we are supposed to make it balanced. For example, there are 3 key elements are there: 5, 10 and 15. Using these 3 key elements, we can make different binary search tree using these 3 key elements. For example, either we can make like this: 5. Since it is a binary tree, the 10 will fall under the right side of 5, and when it comes to 15, it should come under the right side of 10. This is one possible tree. Otherwise, I can make like this as well: 5 and 15, or else 15 can act as a root node, 10 will fall under the left side of 15, and 5 will fall under the left side of 10. Otherwise, 15, 5 and 10, we can make it like this also, or else 5, 15, 10. So like this, several different combinations are actually possible. So out of all this, the better one is going to be, for example, this is the tree, the number 1, this is number 1, 2, 3, 4 and 5, right? So here, if this is the tree, I just want to perform the searching operation. I just want to find the key element 15. If so, the total number of iterations which it is going to take is, first it will check 5, and then it will go to 10, and then it will go to 15. So 3 iterations it will be taking. If there are n number of elements, n number of iterations it is going to take when it comes to binary search tree. And here, when it comes to the second tree, when we check, I just want to, suppose I want to search the element 5. In this case, first it will check the root element. Since the element which I want to search is lesser than the root element, it will directly go check the left hand side. So the 5 is over here. So like totally 2 comparisons we have done here. two comparisons we have done for tree number 2. When it comes to tree number 3, I just want to search the same element, the node which is 5. So here again 3 comparisons I need to do. Again here also if I want to search suppose 10, again 3 comparisons it would take. Here again if I want to search 10 from this tree, again for searching 10, 3 comparisons it is going to take, right? So other than the tree, the second tree, all other trees are taking 3 comparisons, but one tree 2 alone is taking only 2 comparisons. Why? Because tree number 2 is balanced, others are not balanced, that's why. So like it clearly shows that if the tree is balanced, it will be taking only the less number of comparisons, right? So now if the tree is not balanced, how to make it balanced we are going to discuss now. So to make it balanced, we are going to perform rotations. So there are totally 4 rotations are there under AVL tree. The very first one is left rotation, right rotation, left right rotation, and right left rotation, right? So totally 4 rotations are there. So we are just going to choose the appropriate rotation and we are just going to apply it over there to make the tree balanced. Okay, so we'll take the first type. When we check, so there are 4 types are there. I will discuss one by one. So when we take the first tree, this is our first tree, 5, 10 and 15. This is our very first tree. So which rotation we are supposed to apply over here? We need to check, right? So 5 and 10 is the left child node for the node, the root node 5. So left. Then again when it comes to 15, again it's a left child node for the node 10, right? Left. So here we are supposed to perform the left rotation over here. So left rotation in the sense we are just going to pull the 5 down over here. So when we pull the 5 down, now 10 will be acting as the root node and 5 will fall under the left side of 10 and 15 will fall under the right hand side of 5, right? So when we calculate the balance factor, like for calculating the balancing factor, already we discussed the formula here, height of left subtree minus height of right subtree. So before that we calculate the balancing factor for this tree first, right? So like we should start from bottom only, like we should start from newly added node, right? So 15 is the last node, right, which is a newly added node. We start from here only. So the balancing factor for the node 15 is height of left minus height of right, right? There is no right node as well as there is no left node. So the balancing factor for the node 15 is 0, which is balanced because it should be either 0 or minus 1 or 1, right? So we are getting 0. Since we are getting 0 here, the node 15 is balanced. When it comes to 10, height of left minus right, so there is no left subtree for the node 10. When it comes to right, there is 1, right? The height of the right subtree for 10 is going to be 1. So the balancing factor is minus 1, which is again balanced only because we are getting the balancing factor minus 1. So for the node 5, if you calculate, there is no left subtree, so it is going to be 0. When it comes to the right subtree, the height of the right subtree is going to be 2. So 0 minus 2. Minus 2. The balancing factor for the node 5 is minus 2, which is not balanced. So to make it balanced only, we have performed a left rotation, and after performing the rotation, this is going to be our final result. When we compute the balancing factor now, for 5 there is no left, there is no right, so the balancing factor is going to be 0. For 15, no right, no left, so the balancing factor is 0 again, which is balanced only. When we take 10, the height of right subtree is 1, the height of left subtree is 1 and the height of right subtree is 1, so the balancing factor is again 0 here, which is balanced now, right? So this is how we are supposed to perform left rotation. Next, right rotation. For that, to explain right, I am just going to take third example, 15, 10 and 5. Right rotation. if suppose this is the tree, calculate the balancing factor. For 5 it is going to be 0, for 10 it is going to be 1, and for 15 it is going to be 2 minus 0, which is 2, which is not balanced, right? So we are just going to make it balanced. So to make it balanced, we are supposed to perform the rotations only. So when we check right it is, right? So we are supposed to perform right rotation. So if so, we are supposed to pull this 15 down over here, this side. So when we pull like this, we'll be getting the resultant tree like this: 10, 5, then again 15. So when we calculate the balancing factor, for 5 it is 0, for 15 it is 0, then again for 1 it is going to be 0, which is completely balanced. And the third type is left right rotation, which is LR rotation. So for this, I'm going to take this example, fourth one, 15, 5 and 10. Right, when we calculate the balancing factor, 0 minus 0, 0. So here there is no left subtree, but the height of right subtree is 1. So the balancing factor is minus 1. And for 15, the height of left subtree is 2 minus the right subtree. There is no right subtree. So it is 0, which is 2. It is not balanced, right? We are supposed to make it balanced, right? So for right and for left, we just made, like, we just did only one rotation over here. Just if it is left, we just pulled the root node here down. If it is right, we just pulled the root node towards in the right hand side down, right? When it comes to left, right and right, left, we have to perform two rotations over here. The very first step is 15 will be here only 15. So we are supposed to just pull this 10 down over here. If so, just imagine that you're just flipping 10 and 5 like this. So 10 will go here. We are just flipping it. So when we flip it, after flipping it, 5 and 10, right, this 10 is acting as the right child for the node 5, right? When we flip it, it will become like this, 10 and 5. So we are supposed to flip like that. So when we flip it, we get like this, right? After flipping it, then you just pull. Then again you are supposed to apply what? Left rotation. So now 10, 5, 15, like this the tree will come. So two rotations you are supposed to do here. First is flipping these two, and then like either you will get right or left rotation after making the first rotation, and second rotation is going to be very easy. Just pull the root node down. Like if it is a left towards right, you're supposed to pull it. If it is a right, you're supposed to, sorry, this is again left. I'm very sorry, this is going to be right, and this is going to be left. One correction. Okay, you can change it. Okay, so since it is left, you just pull it towards right. If it is right, you're supposed to pull it towards left. Right, so finally the tree is balanced now. And the fourth type is right, left rotation. So for right, left, I'm going to take the fifth tree as example, 5, 15, 10, right? So this is right, and again this is left. This 10 is acting as a left node for the node 15, right? So for this it is 0, it is 1, and 0 minus 2, minus 1, here it is minus 2, which is not balanced. We are supposed to make it balanced. So when it comes to right, left and left, right rotation, we are supposed to make totally two number of rotations, right? The very first is flipping it, right? So here 15 and 10, we are supposed to flip it. So when we flip 15 and 10, it will become like this, 10 and 15 like this. So after flipping it, 5 will be here in the same position only, right? So after flipping 15 and 10, it would be like this, 10 and 15, right? So now it is going to be right? So you just perform right rotation. So now 10 will be here. When you pull 5 down, 5 will come over here, and 15 here. Now when we calculate the balancing factor, for 5 it is 0, for 15 it is 0, and for 10 again it is 0, which is completely balanced. So this is how we are supposed to perform the rotation. So by doing the rotations only, we will be able to make the tree balanced. There is one small correction here. Instead of writing right rotation, I have written here left rotation. Please correct it. And here instead of left I have written right. So I have corrected over here. I'll make it clear. So this is left rotation, right? This is right rotation. Hope this is clear. Thank you.